Hi there, this is Andy Warwick here with the first of 3 videos on the cultural history of theoretical physics. I'm going to be talking about some of my work on mathematical physics in Victorian Cambridge. But I thought I'd start by going back to the mid-1980s when I was a graduate student in history and philosophy of science in Cambridge as a way of giving you some idea of what sort of project this was. At that time, I was just starting a thesis on the Cambridge reception of special relativity. As an undergraduate in physics, I'd been interested in the foundations of physics and in theories of scientific progress, especially Thomas Kuhn's idea of revolutionary theory change, something that I'd experienced myself as an undergraduate moving from classical to modern physics. I particularly like Kuhn's idea of physics as a problem-solving enterprise because that seemed to be the closest to my own experience as a student. My thesis made theory change an historical problem. I hope that the rejection and then acceptance of Einstein's theory of relativity in Cambridge would throw some light on scientific progress. The received account was that Cambridge physicists believed in an electromagnetic ether, and that since Einstein rejected this ether, they rejected him. They were described as irrational or blinkered, and I wanted to find a better story. But the question was, what kind of story would that be? Now, at that time, a new young lecturer had arrived in Cambridge, Simon Schaffer, who was about to publish Leviathan and the Air Pump with Stephen Shapin. And Simon put on a course in the sociology of scientific knowledge for historians. And I found some of the ideas and concepts in this course extremely exciting and with huge potential, I thought, for telling a new kind of story about the history of modern physics. The sociology of science at that time was something of a mixed bag. There was Bruno Latour studying laboratories as an anthropologist might study exotic tribes, following the rat sacrifices that they called experiments, the disputes and micro-interactions by which they made what they called scientific facts. A more sober Harry Collins following attempts to replicate the TEA laser and to find gravity waves, showing experiment was much more than a flip-flop logic to decide upon the truth or falsity of theories. The Edinburgh School of David Bloor, claiming that science wasn't wholly determined by nature, but was in some way socially constructed. I was by turns astonished, perhaps in some ways dubious, but also completely intrigued by these new approaches. I liked the idea of studying science in action, how it was done rather than how philosophers said it should be done. Hearing scientists speak their own words from the cutting edge of research was a revelation. The key message for me was science isn't a place beyond culture, it's a culture of its own, one in which natural knowledge is inextricably linked to the machines and the theories by which it's made. The sociology of science let me step outside of my physics training. It was somewhere else from which to look back and see things that I hadn't seen before. But I think I was a little unusual in wanting to reconstruct rather than deconstruct scientific knowledge. That is to say, I wanted to show how science works rather than how it doesn't. Take, for example, Harry Collins' work on replicating the TEA laser. Replication was supposed to be the touchstone of scientific truth, yet Collins showed that obtaining stable, agreed results was often slow, contentious, loaded with taken for granted theory, materials and techniques. What if you thought about the clash between new and old theories in that way? Theorists don't reject new theories because they're blinkered or irrational, but because their theories are populated with different entities, with different techniques that are taken for granted. What if theory is messy and negotiated too? In the early 1980s, I found this exciting, with the potential to move beyond the dominant history of ideas approach towards the kind of cultural history that was informing other historical specialisms from which the so-called hard sciences had been excluded. And I thought I'd say a little bit about Einstein's special theory of relativity as a way of illustrating some of these points, and some that are going to come in subsequent videos. So in June of 1905, the 26-year-old Albert Einstein published a paper entitled On the Electrodynamics of Moving Bodies, which was the foundation of what we would call the special theory of relativity. And Einstein came to all kinds of really interesting conclusions in this paper, but I just want to draw attention to three. The first is that Einstein began the paper by drawing attention to an asymmetry in electromagnetic theory that he thought wasn't present in nature itself. Namely, that if you have a coil of wire and you take a magnet and push it into the coil, you will get an electric current. If you hold the magnet still and you push the coil onto the magnet, you will get exactly the same current flowing. In other words, all that seems to be important here in nature is the relative motion between the magnet and the coil. But when you look at Maxwell's electromagnetic theory, it gives a quite different account of what happens depending on which one of the two moves. Einstein thought that this was in some way wrong. Now, that's point number one. Point number two is that in order to solve this question, he did something rather unusual. He asked the question, how do we synchronize two clocks that are separated in space using an electromagnetic wave, light, for example? And what he said was that to do this, we have to introduce two new principles into physics. The first was the principle of relativity. That is, that all motion is relative motion, not just in mechanics, but also in electromagnetic theory. The second principle was the principle of the constancy of the velocity of light. That the velocity of light is a constant of nature and will be measured the same by all observers, no matter what kind of state of motion they are in. Now, this solved Einstein's problem, but it had some extremely important implications, which brings me to point number three. One of the very important implications was that space and time are not absolute concepts, but relative concepts. That is to say, they depend upon the relative motion between observers who are measuring space and time. They will measure them differently. Now, how on earth did a 26-year-old physicist who wasn't even in a professional academic job but working in a patent office, how did he come up with such a remarkable solution to this problem, this asymmetry in electromagnetic theory? One answer, and one that I would associate with the history of ideas, is that Einstein was a genius. In other words, his mind or his brain wasn't like yours, it wasn't like mine. He simply had a different kind of mind that was able to see things that most of us simply cannot see. And if you take that kind of approach, the historical problem sort of goes away, because there's really nothing much left to explain. You can set out a chronology of what Einstein did, but you don't need to really give an historical explanation, because the explanation is he is a genius, he is different, he is not like us. So this slide typifies my take on the history of ideas approach, still common in the 1980s. Einstein's route to relativity is explained in terms of his own recollections, depicting his own thoughts. And I've used a box function to represent what I take to be the rather bounded nature of this kind of explanation. The focus is on what goes on inside Einstein's head, namely ideas. The implicit explanation, not by Einstein himself of course, is that these are unique markers of an intellectual journey only accessible to genius. Note Einstein's comments are not contemporary with the development of relativity theory. They were in fact made in 1949, 1946 and 1922 respectively. Historians, of course, have learned to be very skeptical about these kinds of retrospective accounts of theory development. Indeed, I've quoted Einstein's own advice on that topic: study the theoretician's deeds, not their words. And with that in mind, I'm going to apply a kind of historian's Fourier transform to reconstruct this box or mind function in a much wider cultural space. So here's Einstein again in his student and early patent office years, but this time we've moved from his unmediated thought to a range of contemporary resources that he might have used in tackling problems in theoretical physics. At the top left is the ETH Zurich, a place described as the crossroads of European revolutionary movements, especially Russian socialism. Here Einstein's friend, housemate and fellow physics student Friedrich Adler, who later assassinated the Austrian Prime Minister, was trying to combine the works of Ernst Mach with those of Karl Marx. Adler sought the revolutionary overthrow of metaphysics in favour of phenomena. Now, my point here is that Einstein learned his physics in a revolutionary environment, constantly discussing the philosophical foundations of the discipline, an approach he freely used in developing his theories of the electrodynamics of moving bodies. And as we'll shortly see, this was a very, very different atmosphere from that in late Victorian Cambridge. Bottom right is Marcel Grossmann, Einstein's friend and fellow undergraduate at the ETH, who lent his friends notes on the lectures that Einstein frequently missed. You can see Einstein's jottings as he worked his way through the lectures. And here my point is that Einstein's conception of the physical world in terms of theory and experiments was learned. For example, you can see August Förpel's textbook on electromagnetism, which Einstein used, in which Förpel set out exactly the paradox of relative motion in Maxwell's theory of induction that Einstein used to begin his paper on the special theory of relativity. Bottom left are the core members of the Olympia Academy, Einstein's group of friends with whom he met to discuss philosophical aspects when he was working at the patent office in Bern. Einstein described one member, Michel Bessot, as the best sounding board in Europe for scientific ideas. They famously discussed the problem of absolute time just before Einstein put together the final pieces of his special theory of relativity. The paper cites no other physicists, only Bessot for several valuable suggestions. So special relativity wasn't simply an idea in Einstein's mind, it was part of an extended discussion with his philosophical fellows. What about the patent office itself? Around 1900, the problem of coordinating distant clocks by telegraph or radio had become a major issue on which numerous patents were filed. You can see one on the top right. Einstein worked in the section in which they were examined. The office itself had numerous coordinated clocks, as did the town of Bern. Indeed, Bern was the centre of the clock coordinating industry. Einstein actually pointed to two such clocks as he explained his revision of the notion of absolute time to his friend Bessot. So Einstein didn't simply work in the patent office while he was doing his physics. His job was to consider the originality and the clarity of the principles at the heart of new electrical devices, including electromagnetic coordinating systems. It was the exciting possibilities of using this kind of broad and detailed research to escape the closed box of ideas that drew me to cultural or constructivist accounts. Einstein is remade not as a cipher who divines truths by the insights of genius, but as a brave and creative young man using the resources of his time and place. Indeed, he later described himself as an unscrupulous opportunist. Now, I'm not going to go through the case of special relativity in detail because it wasn't research that I did. I will leave some references in the links below. Instead, I'm going to move on to talk about some of my research on mathematical physics in Victorian Cambridge. So I'll see you in the next video.